Welcome to Building Scalable Distributed Systems, Week 8, where we're going to start talking about the data layer, which is a foundational area of scalable distributed systems. We're going to look at some foundational issues to do with scaling the data layer. Talk initially about how we scale existing databases, relational databases, and the difficulties inherent in that. We'll then talk about partitioning and replication, which enable us to distribute data across multiple nodes in a distributed system. And then once we do that, we have to deal with the issue of consistency. And that's the final topic we'll talk about today. So let's start by talking about the issue of scaling existing relational databases. Relational databases are a really well-established technology. They've been around some 30 years or so now. They're based on a well-understood model of the relational model, which has a defined schema and query language, SQL, which we all know and love. The 30 years or so that these technologies have been around have enabled the vendors and the open source providers of these technologies to make them highly optimized, very stable, full of features, and really robust systems. And we can scale them up really easily by running the database on just bigger machines, where we throw more memory, more CPUs, and more disks at the actual database engine. There's many competing engines that you can choose from, both open source and commercial, and these you will find a relational database probably in every IT shop you stagger into anywhere in the world. Scaling up is really simple with relational databases. You just buy a bigger machine. Here's an example of a machine that has 32 terabytes of memory, network sockets, massive amount of bandwidth to be able to transfer data in and out. It has multiple CPUs, and it has this optimized NUMA memory access scheme, which makes access to local memory much faster than shared memory, which is really appropriate on server machines such as database engines. So this is probably, when you listen to this, probably an old machine. You can buy much bigger ones now, or you can provision a much bigger one on your favorite cloud. But this is basically how you scale up a relational database. These things aren't cheap. So you can scale up by buying a bigger machine. Once you get to the stage where you've spent enough money on your machine, you might want to start thinking about adding multiple disks to the machine. If you have multiple disks, you can then partition your database. An expert's database administrator will partition your schemas and your tables across different disks and enable you to query the data that's on different disks in parallel. And this gives you some better performance. And then if you want to go further, you can split your database, split your schema across multiple machines, as the bottom example shows here. So we basically partition our database across multiple nodes, and this gives us some sort of ability to query both databases at the same time and get more throughput. Typically you'd do this using some sort of functional partitioning, as the slide says here. You'd have customers and orders maybe in one database and stock in another database running on a different machine. Disadvantage of this, of course, is you need to buy more machines, and if you're paying a license to someone like Oracle, then you actually pay more money to actually deploy your database. Another way we can scale a relational database is to use a technique called read-write splitting, whereby, as you can see on the slide here, we have a primary database copy, which can accept writes and potentially reads too, but the primary copy is then copied to a replica, which is only available for reads. This means we can send many of our reads to the replica and dedicate most of our writes, all of our writes, and potentially some reads to the primary. This offloads the responsibility of doing many reads from the primary copy of the database. The way the two are kept consistent is through some sort of asynchronous replication scheme. So a write will be written to the primary and then copied to the replica. This means there's some sort of delay here, and This is the replication latency mentioned on the slide. So it's possible that you may read something from the read replica that is actually not up to date in the primary. This is known as the inconsistency window, and something we'll talk about considerably more later in this week's materials. Various strategies are adopted for scaling relational databases. This slide shows you an example of Oracle's RAC system. Here you can see that the Oracle database engine runs on multiple nodes, so we have multiple querying engines running queries in parallel, and all of these engines have a shared data store known as a storage area network. This is a highly optimized network attached storage array which is shared across all of the database engines. In contrast, you can have MySQL's cluster architecture, which is a shared nothing architecture. This means that there are multiple database engines, but basically each has its own portion, its own partition of the database. And so when a query comes in, the engine is responsible for finding the data that's being referenced by hashing the primary key of the data to find the table and the actual node where the storage is attached. So there's two contrasting ways you can have a shared nothing or a shared everything style architecture for scaling a relational database. More generically, the approach used by the MySQL cluster is known as sharding. And what sharding means is that we can partition our data across multiple database engines. So on the slide here we have an example of the data for Europe being stored on one database engine, the data for America being stored on another, and the data for Asia being stored on another. When we look up an item of data, we basically use its key to locate where the data is stored. So there's some function, typically a hash function, but it doesn't have to be, that the shard lookup will say which shard, which partition is the data that I want to access stored in. And so this is an extremely appropriate way for distributing data across multiple database engines. The issues, of course, are you evenly distributing data across the engines in terms of the read load, the write load, maybe even the data volume? This example, we may have many more customers in Asia than we do in Europe. And how do we handle a failure? Maybe we try to access the Americas shard, but there's a network partition and we can't see that at the time that we're trying to do some sort of join with the Americas and the Asia nodes. So it's a distributed system, failures can happen, we have to be able to handle them. So in general, relational databases were designed originally to provide really flexible data modeling and query languages that can accommodate this broad range of queries. Because SQL is a powerful language, we don't have to anticipate every query that someone can ask of our data. And when we normalize our databases into a relational database, we're providing a structure that can be flexibly queried using the power of SQL and typically the ability to join data together from different tables. So this is a very powerful technique, and we can scale this up on expensive hardware as we've talked about already. But joins present an interesting problem when we scale out our data across multiple machines on cheap hardware. So just normal nodes that we have disks attached to and we partition the data across. First of all, how do we partition that data? We have to have some sort of shard allocation scheme, typically through hashing. But if the data is randomly distributed across multiple nodes and someone tries to execute a join, then potentially that join is going to be accessing data that resides on disks attached to multiple nodes, maybe many hundreds of nodes in our system. So how do we implement a join efficiently on a distributed database? Turns out it's hard, and a really good example of scaling and the difficulties of it is from Facebook. Facebook originally, back in 2007, if I remember correctly, built their infrastructure for storing all our Facebook information on MySQL and had caching using memcached. This meant scaling was extremely hard as their penetration into the social media community grew, and there was extensive master-slave or primary, secondary, as it's more commonly known, sharding across data centers. And so we would be sending reads to the secondaries and writes to the primaries. And basically this meant because the data was so widely distributed, then joins across shards became really difficult to implement. So Facebook, with their engineering might, built a layer on top of MySQL known as Tau, which is basically a custom graph database layer. And if you think about social media networks such as Facebook, all our data is a graph. I have many friends, they have many friends, so it just naturally forms a graph. And underneath Tau, the API that the application developers use maps to the SQL queries, which are optimized for a 500-to-1 read-write ratio. So with your Facebook, you can do this kind of thing. Not everyone can, and maybe we have to approach the problem somewhat differently. Other considerations, as we said, relational databases are conceived to store data in a flexible way, and they were originally designed to store business data, things like banking data, insurance data, customers and orders. And this sort of stuff needs to be correct and it needs to be up to date. It also needs to be consistent, and we'll come back to the issue of consistency in much more depth later in this week and next week's material. We also need to be able to recover from failures. So if our single node fails, we need to be able to restart the database and read through the transaction log and replay any transactions that were not fully persisted to our store. And that turns out to be a lot of complex logic that runs inside a database engine. But as the internet grew, as we talked about, from about 2006, different business models grew on the internet. Nobody designed relational databases to store Twitter data or images or social graphs or log files and transactions flying from devices on our wrists or whatever. And so different types of data grew, which is less critical. Who cares if you lose a Facebook update? It's not the end of the world. But if you lose $1,000 deposit to your bank, then, nobody's happy. So what's happened is, as the internet has grown and the problems that we have to deal with grow in size and differ in nature from the original business problems, we've evolved a new set of database technologies. And we'll talk extensively about these in this course. There's 4 basic models which are shown on this slide. Key value, just a hash table. Graph, you know what a graph is. Column family is kind of a key value, but it's a different take on the way that you implement a hash table. And a document is like a JSON style database that enables us to store documents that can reference each other within the actual persisted data store. And we'll talk about different databases that implement these models in the next couple of weeks. Collectively, these databases are known as NoSQL, and this name arose a decade or so ago from the database community to just talk about databases that weren't based on the SQL model. And they were designed typically to scale horizontally and provide performance and scalability that can be implemented on commodity hardware. You don't need to go out and buy your $3 million super big multi-processor huge disk storage machine. You can just go out and buy 100 normal commodity nodes and distribute your data across those, and the database engine will efficiently utilize all of the CPU and disk resources that you have. So there's different data models. All NoSQL engines implement a different data model. Typically, they have their own query language. How you scale the beast varies from database to database, and they have different consistency models, as we'll talk about soon. So the whole world of NoSQL is very different and complex to the world of SQL, which you may know and potentially love. So distributed databases was driven by, first of all, the move to scale, as it's known, big data, problems that generated so much data we couldn't even conceive of storing them on the same disk or the same machine. Also economics, these huge servers that we talk about when we discuss scale up are really expensive to buy. If you need to buy many of them, and it's millions and millions and millions of dollars. Whereas that using cloud systems that we now have available to us, we can just provision many low-cost machines really easily in data centers and distribute our data across them using one of these distributed database engines. This means we can throw more resources at a problem, more CPU, more disk, and scale out our processing engines to exploit potentially thousands of machines. And this is really important. Also gives us increased availability because we've scaled out. If we distribute our data wisely and maybe have more than one copy, then we can provide very high availability if there's a failure to the data center where our data is stored. So here's a picture on the bottom right here of an area of Washington State where it's an old rural area, but it's basically now populated with data centers, and you can see Microsoft, Intuit, etc. all have their data centers here. These data centers are huge buildings, huge warehouse type buildings, just full of racks of machines as shown in the illustration here. And they're located in areas, in this case an area of Washington State which is very close to the Columbia River and a very large dam which generates cheap hydroelectric power. So this is when you're accessing Microsoft's Azure, or there's a Google data center not far from here. This is where the actual processing for your queries is taking place in data centers such as these. And as this slide shows you, this is an oldish slide from 2016. The whole database landscape is incredibly complex. There's different models. There's the relational zone in the middle. There's non-relational. There's graphs. There's grid and caching. Things like Redis and Memcached, which we discussed earlier in this course, would live in there. And there's this whole area of distributed documents and hash table, key values type stores. So database selection for your scalable application is a non-trivial exercise. So we scale our database layers by breaking it up into multiple chunks and distributing the data across multiple machines. And to achieve availability, we have multiple copies. So if one copy of the data is unavailable because it lives on a machine which has died, we can find another copy somewhere. So partitioning and replication are the two issues that we'll now talk about. There's two basic architectures for achieving this partitioning and replication. One is known as leader-based, where we have a main copy of the data and we replicate copies to other machines. So this is a bit like the read-write splitting that we talked about earlier. Again, this was originally called master-slave, but we don't use those terms no more. But you will see it extensively within the literature. The other one is leaderless, or peer-to-peer, where there's nothing shared. Every node has its own portion of the database, and if you want to access that portion of the database, you have to talk to that particular node. And here you can see there's a database called REAC which implements this peer-to-peer, also known extensively in the literature as masterless architecture. And the strengths and weaknesses of each, as hopefully you're starting to gather from this course, there's no right or wrong answer. So in our leader-based architecture, we have one leader and potentially many followers. All writes go to the leader and reads can go to the leader, but they typically will all go to the followers. The strengths of this, of course, is we have a single copy of the data, the truth, which is stored in the leader. So if we want to get the latest version of any particular data item, then we can know where it's stored. And this can also means we can offload all reads to the followers, and this reduces the load on our leader because it's just handling writes. So this increases the performance and scalability and the capacity of our system. The weakness of this, of course, is that when a write is applied to the leader, it's going to take some time to be replicated to all of the followers. and potentially it could be replicated to some of the followers at some stage, some moment in time, but not all of them, which means reads may be dependent on which follower a read is directed to. The other downside of this, of course, is the bottleneck of writes at the leader. If there's so many writes our leader can't handle the load, then what do? You can't write to the followers, so you have a problem there. And of course, if the leader were to fail or be unavailable, then the system just becomes read-only until the leader is restored. So, strengths and weaknesses. We can extend this basic scheme as shown on this slide here. The top diagram shows that we can replicate our leader, or our master as it says on this slide, so that we have two copies and these stay consistent. So we can direct writes to either the first copy or the second copy, and then the two leaders will replicate the writes across themselves, and these writes will then be propagated to each of the followers that they manage. So there will be a delay, but writes made to the second leader here will eventually propagate to all of the followers managed by the first leader. You can also partition the database so that each leader actually handles a different partition of the database, different chunk of the database, and that is then replicated to multiple followers for reading. So then writes can be directed to the appropriate master using some sort of sharding mechanism, a hash key essentially. And then all reads for that portion of the key space can be directed to the followers, which are managed by that particular leader. So there's various ways of scaling this out. The top one here provides enhanced availability for writes and enhanced scalability for reads because there's many more followers. And the bottom scheme here basically provides enhanced scalability. Now, one complexity that arises with leader-follower type architectures is what happens if the leader fails. The machine might crash, it might be unavailable due to a network connection being down to the leader. So if we can't have a leader, we can't make any writes. And if that leader is down for a long time, then the system just becomes read-only, and that may not suit many business cases. So we want to be able to elect a new leader from our followers, because the followers all have a mostly up-to-date copy of the database. So this seems conceptually pretty darn easy. We just need to choose a new leader from our followers. So if we have 4 followers, then we just choose one as leader and the other 3 remain followers. So how hard can it be? Well, remember the 2 generals problem? And we talked about consensus in distributed systems in week 3 or 4 of this course. And the basic summary of that is that given the 2 generals problem and there's no 100% message delivery guarantee, then how do we achieve consensus in a distributed system? If you think about it, electing a new leader from 4 followers means that all of the 4 nodes need to agree on a new leader, such that once a leader is elected, there is 1 leader and 3 followers, and all of the nodes need to have a consistent picture of this scheme. So the election of a new leader is essentially a consensus problem, and as we know from the 2 generals problem, this is a hard thing to solve. So let's think through how new leader election can happen conceptually. We have a leader-follower system, or primary-secondary as it's called on this slide, and the leader, the primary, dies. First of all, how do the followers detect this? Say we've got multiple of these, maybe 7. Which one detects it first? How do they detect it? Typically this would be done by sending background network messages like pings to see if the leader is still alive, and if it doesn't respond for a series of these, then one of the followers will assume that the leader has died and start an election. Once an election started, it must satisfy both safety and liveness properties. What does this mean? It means only 1 node can be elected leader. If we have multiple leaders elected from our election, that's bad. Think of the presidential election that's coming up as I record this. We wouldn't want Trump and Biden both elected as leader. You know, it might happen. We also want to make sure that every node, once the election is completed, is either a leader or a follower. We don't want any node to still be in this limbo state of thinking there's an election still going on. So that's the liveness property. That means once they are in a leader or a follower state, then the system can continue. So this selection process is fraught with issues. For example, what if the followers can't see each other through some sort of network partition? We have two followers that can communicate with each other, but we have three others that can't communicate with those two due to a network failure, a network partition as it's known. And this is known in this particular problem as a split brain problem. The two halves of the partition can't talk or agree on the state of the system. And what happens if we have a leader that was simply unavailable? The network died for 20 seconds. And while the election is going on, all the leaders and the followers, are negotiating who should become the next leader. The original leader comes back and says, "Hey, I'm here. I've just accepted a few more rights. Here they are. Apply them to your copy of the database." What happens? It's complicated. So let's take a look at a relatively simple leader election algorithm known as the bully algorithm. It's one of the original ones. There's many more sophisticated and reliable ones than this, which we'll talk about briefly in later classes. So the basic assumption is that we can detect a failure of a system through a timeout, i.e. one of the nodes sends messages to others, and if it doesn't receive a response within a given time period, it assumes that the node has failed. We have a closed set of nodes that can be either leaders or followers, and each node has a unique identifying number. And every process knows how many other nodes there are in the system. So as I said, it's a closed group. But processors don't know which other nodes are alive and which are not. So they have to figure out the collective state of the system by exchanging messages to see which systems respond to messages and which don't. And when an election is held, the process with the highest process number is elected as the leader, the coordinator, and it's agreed on by all the other nodes, all the other processors. So if we have numbers 1 to 7 nodes, then if all the nodes are alive, then the algorithm will guarantee that node number 7 is the leader. Let's see how this works. Here's a little example of our system. We have here P0 to P6. So this means that, according to our algorithm, P6 is our leader. Let's assume now that P6 fails. Our task is now to elect a new leader from the existing nodes in the system. So as all the nodes are sending messages to each other to find out which ones are alive and which aren't, we don't know which one will detect the failure of P6 first. So in this slide, P3 is the one which detects that P6 has failed, and it then starts an election. And the election algorithm states that if I'm Pn, I send a message saying I'm starting an election to all of the processors with a higher n than myself. So in this case, P3 sends messages to P4, P5, and P6 saying, "We've lost our leader, we need to start an election." All of the processes that receive this election message will respond, if they're alive, with an OK message. And so in this case, P6 isn't alive, so it doesn't respond, but P5 and P4 are, and they both say, "Okay, P3, we're still alive, we're happy to participate in this election." So next, P4, because it's received an election notification from P3, and P4 is obviously higher than P3, it can now start its own election bid. And in this case, it sends the election message to the nodes with higher numbers, P5 and P6. Only P5 will respond because it's the only one alive. P6 is still failed. And so P4 says, "Okay, I can't be leader because P5's around." And so P5 will now start its own election. It will send a message to the nodes with higher numbers than itself, in this case P6. P6 is still failed because it doesn't get a response from any nodes within a timeout period. It can now assume that it's the leader, and it tells all the other nodes that it is now the leader. And that's how the bully algorithm works. And this is a simple algorithm and not suitable for real systems, but it's good to illustrate the concepts. The complexity, if you think about it, the worst case complexity is, in terms of message exchange, is when the lowest numbered node detects that the leader has failed. So if P0 in that case detects that P6 has failed, then it will cause the most message exchanges, and this tends to be order n squared. The time to make a decision, it's very dependent on the timeout period that's used. And what happens if in our example, P6 is flaky? And by flaky, I mean it's alive for 5 seconds, and then the network dies, but it comes back to life 5 seconds later, and then it dies again. So we have this transient network failure scenario. How does the algorithm handle that? Well, it turns out it's not well. If you think about it, it can start flipping because P6 is alive, it's suddenly the master, then it's not, there's an election going on, then suddenly it comes back to life, and things get horribly complicated. Also, we talked about the split brain problem earlier. So what about if there's a network partition where half of the nodes are in one half of the network partition and the other half in the other, so such that they can't see each other? This means that they could both partitions could potentially trigger their own election, elect their own local leader, and then when the partition heals, we have two leaders and chaos ensues. Not good. So leader election is an example of an algorithm which requires consensus in a distributed system. As we talked about, starting with the two generals problem, this is actually a really difficult problem to solve because multiple servers need to agree on the shared state, i.e. who is the leader, in the face of many potential failure modes. And so we'll come back to this issue in depth next week, I believe. There's a number of algorithms. There's a good summary of them on the top link here on Wikipedia. Paxos we'll talk about briefly, which was the most famous original consensus algorithm. And then we'll give an example in much more detail of an algorithm called Raft, which tends to be more practical to deploy than Paxos. And if you want to see a sort of good practical compromise between all of the theoretical approaches that we'll talk about, then MongoDB has a good description of its consensus algorithm at this link here. So the alternative to leader follower is our peer-based replication, or leaderless. In a leaderless database, there is no master copy where all writes have to be sent to. Any node can accept a write, and data is replicated across nodes such that when a write is accepted on one node, it then propagates the copy of that data, the new copy of the data, to all of the replicas within the database. It can do this either synchronously, so it can send out a message and wait for the updates to be applied, or it can do it asynchronously. It can accept the local update and propagate the updates to the other nodes asynchronously, meaning there's some sort of window of inconsistency. So this in many ways simplifies our problem because we don't need to have an elected leader, but it complicates it in other ways too, as we will see. So peer-based replication has the advantage that we can write to any node. So all nodes can accept writes, which improves our write throughput. But the problem is, how do we keep all the copies of the data consistent? So we have to deal with the issue of replica consistency. And that is the topic of our next lecture.